There's a Kubernetes cluster out there right now burning $10,000 a month on GPU nodes that sit idle 60% of the time. Why? Because the scheduler can't say only schedule pods on nodes with more than 4 GPUs. It's 2026, and our scheduler still can't count. But that's about to change. Today, we're talking about 2 alpha features in Kubernetes 1.35 that represent a fundamental shift in how Kubernetes handles scheduling and storage: extended toleration operators that finally let the scheduler do math, and mutable persistent volume node affinity that lets storage topology adapt to reality. Plus, we'll connect this to the bigger picture: Kubernetes evolving from reactive feedback loops to truly predictive infrastructure.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into Kubernetes' upcoming features, specifically extended toleration operators for numeric comparisons and mutable persistent volume node affinity. Both are alpha in Kubernetes 1.35, both solve real operational pain points, and both are part of Kubernetes becoming smarter and more adaptive. Let's start with the news.
First up, Percona just made a major strategic shift with their database platform. OpenEverest is becoming OpenEverest with open governance and multi-vendor support. They formed a new company called Salonica to lead development, and they're positioning it as the first truly open-source multi-database platform for Kubernetes.
This supports MySQL, PostgreSQL, MongoDB, and Velki, right? And it's modular architecture, so you can mix and match database engines and storage backends.
Exactly. The big deal here is open governance. Database operators have been maturing, but most were single-vendor solutions. OpenEverest is positioning for CNCF involvement and ecosystem growth. For platform engineers, this means you can standardize database provisioning across technologies without vendor lock-in.
The modular approach is key. You're not buying into one vendor's entire stack. You can use the operator that fits your database engine, the storage backend that fits your infrastructure, and the deployment strategy that fits your risk profile. That's the maturity we need in the database operator space.
Next, on the security front, Google just launched Agent Sandbox for GKE, and this addresses one of the biggest risks in AI agent deployments. How do you safely execute untrusted code generated by large language models?
Standard containers share the host kernel, which is a single point of failure. If an AI agent generates malicious code and you execute it in a regular container, you're one kernel exploit away from cluster compromise.
Agent Sandbox uses gvisor to provide kernel-level isolation. It splits the workload into 2 components: the Sentry, which intercepts all system calls and acts as a fake kernel, and the Gopher, which brokers all file system operations. The untrusted code never touches the host operating system.
And for workloads that need even stronger isolation, they offer Kata containers, which runs each pod in its own lightweight virtual machine with hardware-enforced isolation.
The performance optimization here is impressive. They support pre-warmed sandbox pools that deliver sub-second latency, which is a 90% improvement over cold starts. Plus, pod snapshots technology lets you save the state of running sandboxes and restore them near instantly when an agent needs them.
That's the key to making this practical. If every AI agent invocation required spinning up a VM, you'd be waiting minutes. But with pre-warmed pools and snapshot restore, you're getting VM-like isolation at container speed.
And it's being built as an open-source Kubernetes SIG apps subproject, hosted under Kubernetes SIGs/Agent Sandbox, so it'll be usable on any conformant Kubernetes cluster, not just GKE.
Though the highest performance features like pod snapshots and managed pre-warmed pools are GKE exclusive, at least initially.
Now, security alert. We've got a high-severity MongoDB vulnerability with active exploitation in the wild. CVE 2025-14847, dubbed MongoBleed after Heartbleed vulnerability.
This affects MongoDB's zlib-based network message decompression, and it's been in the code since 2017. The flaw is an improper length handling during decompression. When processing undersized or malformed payloads, the system returns the allocated buffer size rather than the actual decompressed data length, which exposes adjacent heap memory to attackers.
CVSS score 8.7, high severity. This is unauthenticated remote exploitation with low complexity. No authentication or user interaction required.
And the real-world risk is significant. Approximately 87,000 potentially exposed servers worldwide, according to Census. 42% of cloud environments contain at least one vulnerable MongoDB instance, and active exploitation is confirmed.
Action items for platform engineers? Update immediately to patched versions. MongoDB 4.4 through 8.0 are supported and have patches. If you can't patch immediately, disable compression as a temporary mitigation and restrict network access to MongoDB instances. And note that end-of-life versions like 3.6, 4.0, and 4.2 will not receive patches.
This is similar to Heartbleed in that it's a memory exposure flaw in a compression library. Credentials, tokens, session data, any confidential information in MongoDB's memory is at risk. Treat this as critical.
Next, predictive capacity planning. This ties directly into our main topic today. The industry is shifting from reactive infrastructure to proactive.
Traditional autoscaling in Kubernetes is reactive. The horizontal pod scaler responds after a CPU spike occurs. The cluster autoscaler adds nodes after pods are pending. Everything is a feedback loop. Problem happens, system reacts, eventually becomes stable.
Predictive scaling analyzes historical patterns, forecasts demand, and scales preemptively. Machine learning models identify anomalies and predict capacity issues before they impact users. This is what people are calling self-driving infrastructure, clusters that self-correct inefficiencies autonomously.
Some teams are using reinforcement learning for autoscaling, which provides learned anticipation based on observed trends. It's not true prediction, it's anticipation. The system learns that every Monday at 9 a.m. traffic spikes, so it scales up at 8:45.
And this is the context for today's features. Kubernetes is moving from feedback loops to anticipation. Extended toleration operators enable smarter initial placement based on thresholds. Mutable PersistentVolume Node Affinity enables dynamic optimization as storage topology changes.
It's all connected. The platform is getting smarter.
And finally, a reminder about platform engineering fundamentals. Your internal tools are products and developers are your customers. Building in isolation without user input leads to adoption flatlines. Forcing adoption through mandates creates resentment and shadow IT.
Build something developers want to use, and adoption takes care of itself. Validate assumptions with real users before building. All these Kubernetes features we're discussing today are useless if platform teams don't build tools that solve real problems.
Features enable capabilities, but adoption requires solving actual pain points. Keep that in mind as we discuss these upcoming features.
All right, let's dive into the first major feature, extended toleration operators. But before we get into what's new, we need to talk about how Kubernetes scheduling works today, because the current system reveals fundamental limitations.
So, taints and tolerations are Kubernetes' way of controlling pod placement. A node taint marks a node as unsuitable for most pods. A pod toleration says, I can tolerate this taint, so it's okay to schedule me there.
And today, there are two operators for tolerations. Equal, which requires an exact match of both key and value, and exists, which just checks if the key exists regardless of value.
Let's say a node has a taint, GPU equals true, with effect no schedule. To schedule a pod on that node, the pod needs a toleration with key GPU, operator equal, value true, and effect no schedule. Exact match required.
But here's the limitation. This is binary. Either you have GPUs or you don't. Either you're a spot instance or on demand. There's no nuance, no thresholds, no numeric comparison.
Right. The exists operator is more permissive. It just says any value is fine as long as the key exists. So you could have GPU equals true, or GPU equals false, or GPU equals banana, and a pod with operator exists on key GPU would tolerate all of them.
Which brings us to the real-world problem. Imagine you have a heterogeneous GPU cluster. Some nodes have 2 GPUs, some have 4, some have 8. You want to say this training job needs at least 4 GPUs per node. How do you express that with equal or exists?
You can't. The value is numeric, so equal doesn't work unless you create separate tolerations for every possible value. And exists is too permissive. It would match any node with the GPU count key, regardless of whether it has 2 or 8 GPUs.
The current workaround is to create separate node pools with labels, then use complex node affinity expressions, and maintain this manually as your cluster grows. It's operational overhead that doesn't scale.
And this problem shows up everywhere you have numeric thresholds, not just GPUs.
Exactly. Spot instances with failure probabilities 0 to 100. You want to say, I can tolerate up to 5% failure rate. Cost optimization, schedule batch jobs on nodes cheaper than 50 cents per hour. Performance guarantees, need nodes with disk IOPS above 10,000. Memory ratios, require nodes with at least 4 gigabytes of RAM per CPU core.
All of these are numeric comparisons, and Kubernetes can't express them with taints and tolerations today.
Now, you might ask, doesn't node affinity support numeric comparisons? It has greater than and less than operators.
It does, but node affinity lacks the operational benefits that taints and tolerations provide. Node affinity is per pod. To keep most pods away from risky nodes, you'd need to edit every single workload. That's hundreds or thousands of pod specs.
Taints invert the control model. The node declares its characteristics via taints. Most pods can't schedule there by default. Only pods with explicit tolerations can opt in. It's secure by default.
And taints support the no-execute effect with toleration seconds, which enables eviction. Node affinity has no eviction capability. If a spot instance receives a termination notice, you can update the taint, and pods without matching tolerations get evicted based on toleration seconds. That's graceful draining based on dynamic conditions.
You can't do that with node affinity. It's evaluated at scheduling time only, not continuously.
So, Kubernetes 1.35 introduces KEP 5471, Extended Toleration Operators for Threshold-Based Placement. This is alpha, feature gate disabled by default.
2 new operators, GT, which stands for greater than, and LT, which stands for less than. But the semantics are about what the pod can tolerate, not a direct comparison.
Let's break that down. GT means the toleration matches if the taint's numeric value is less than the toleration's value. LT means the toleration matches if the taint's numeric value is greater than the toleration's value.
Wait, that sounds backwards. GT matches when the taint is less than the tolerance?
It's about the pod's tolerance threshold. GT means I can tolerate risk up to this level. So a pod with operator GT and value 10 says I can handle nodes with risk 1 through 9, but not 10 or higher. The taint value must be less than the tolerance threshold for a match.
Okay, so it's not taint is greater than value, it's I can tolerate values up to this threshold, which means taint's below this.
Exactly. Let's walk through a practical example, spot instance scheduling. You have a cluster with mixed spot and on-demand nodes.
On-demand nodes get a taint, node.kubernetes.io/SLA equals 100, effect no schedule. That's 100% reliability.
Spot tier run nodes, SLA equals 95, effect no schedule. 95% reliability, some interruption risk.
Spot tier 2 nodes, SLA equals 90, effect no schedule. 90% reliability, higher interruption risk.
And a critical production service needs high reliability. It specifies a toleration, key node.kubernetes.io/SLA, operator GT, value 98, effect no schedule.
Operator greater than value 98 means I can tolerate nodes where the SLA is greater than 98. So nodes with SLA 100 match because 100 is greater than 98. Nodes with SLA 95 don't match because 95 is not greater than 98.
Result, the pod only schedules on on-demand nodes with 100% SLA. It avoids spot instances entirely.
Now, a cost-optimized batch job that can handle interruptions specifies operator greater than value 85. This matches any node with SLA greater than 85, 90, 95, 100. The scheduler picks the cheapest available, which is likely a spot instance.
And that's how you implement tiered scheduling based on SLA without maintaining separate node pools or complex node affinity rules.
Now let's talk about the lesser than operator with a GPU example. You have nodes with 2, 4, and 8 GPUs. Each node gets a taint with GPU count equals the number.
An ML training job needs a minimum of 4 GPUs per node. It specifies operator less than value 4.
Less than means the required value is less than the taint value, so it matches nodes where the taint is greater than the toleration value. Taint GPU count equals 4. 4 is not greater than 4, so actually, wait, let me reconsider.
This is where LT gets confusing. LT value 4 matches taints where the value is greater than 4, so GPU count equals 8 matches, but GPU count equals 4 does not match, and GPU count equals 2 does not match.
That means our training job that needs at least 4 GPUs would only match 8 GPU nodes, not 4 GPU nodes.
Actually, I think we need to clarify the semantics. Let me reread the KEP. Operator LT with value 4 should match taints with values greater than or equal to 4, not strictly greater than.
Or maybe the semantic is inverted. LT value 4 means I require at least this threshold, so it matches nodes at or above that threshold.
Let's go with the practical interpretation from the KEP examples. For threshold-based placement, you'd use operator greater than for SLA-style semantics, where higher numbers are better, and operator less than for capacity-style semantics, where you need a minimum value.
So a better example, nodes are tainted with spot termination probability equals 10 for 10% termination probability, 20 for 20%, etc. A pod specifies operator less than value 15. This matches nodes with termination probability less than 15, so 10% nodes match, but 20% nodes don't.
That makes more sense with the LT semantic. The pod can tolerate nodes with low termination probability.
The key takeaway, test these operators thoroughly in dev environments, because the semantics are about tolerance thresholds, not direct numeric comparisons. The KEP documentation has detailed examples.
Now let's talk about where this gets really powerful: no execute taints and dynamic eviction.
Imagine a spot instance receives a termination notice. You have a 2-minute warning before the node goes away.
A controller updates the taint, node.kubernetes.io/SLA equals 0, effect, no execute, 0 reliability, node is terminating.
Pods with GT tolerations re-evaluate. A pod with operator GT value 85 says I can tolerate SLA greater than 85. SLA is now 0. 0 is not greater than 85. No match. The pod gets evicted.
If the toleration includes toleration seconds, 120, the pod has 120 seconds, 2 minutes, to gracefully shut down before being force-killed.
And the scheduler immediately stops placing new pods on that node because they can't match the SLA equals 0 taint.
This enables graceful draining based on SLA changes, not just binary spot versus on-demand. You could have multi-tier spot with different risk levels and different eviction policies.
And all of this is declarative. You're not writing custom controllers to watch spot termination notices and manually drain nodes. The scheduler and kubelet handle it based on taints and tolerations.
Now, this is alpha in Kubernetes 1.35, FeatureGate Extended Toleration Operators disabled by default.
Not production ready. APIs may change in beta, but it's worth testing in dev and staging to prepare for beta in 1.36.
All right, let's shift to storage. Kubernetes has a similar limitation with persistent volumes. They're locked to specific zones or nodes, and you can't change that after creation.
PersistentVolume Node Affinity expresses that volumes aren't equally accessible by all nodes. The classic example is zonal disks. An EBS volume in US East 1A is only accessible by nodes in that availability zone.
This is set in the PersistentVolume.Node Affinity field. CSI drivers set this during volume provisioning. The scheduler uses it during pod placement to ensure pods only land on nodes that can access their volumes.
And the problem is that this field is immutable. Once set, you can't change it.
But storage technology has evolved. Cloud providers now offer regional disks that are accessible from multiple availability zones. AWS supports live migration from zonal EBS to multi-AZ. Google Cloud has regional persistent disks. Azure has zone redundant storage.
So the real-world scenario is you start with a zonal EBS volume in US East 1A because it's cheaper and your initial workload is small. Business grows, you need high availability across multiple zones. AWS supports live migration of IO2 volumes from zonal to multi-AZ.
But after migration, the persistent volume node affinity still says only US East 1A. The volume is accessible from US East 1B and 1C now, but Kubernetes doesn't know.
Your options are delete the PV and recreate it, which causes downtime, or live with stale metadata and manually manage pod placement.
And there's a disconnect with volume attributes class. VAC graduated to GA in Kubernetes 1.34. It allows modifying volume attributes like IOPS, throughput, and storage type without disruption.
So you can trigger a migration from GP3 to IO2 or increase IOPS from 10,000 to 20,000, all using VAC. But you couldn't update node affinity to reflect that the volume is now accessible from multiple zones.
It's like upgrading your car engine, but the registration still says it's a 4-cylinder. The metadata doesn't match reality.
And from the CSI driver perspective, this is a problem. The CSI driver performs the migration, the volume is now accessible from more nodes, but the driver has no way to signal this to Kubernetes.
The scheduler might avoid scheduling pods on newly accessible nodes because it thinks the volume is still zonal. Or worse, if you manually updated pod affinity, the scheduler might try to schedule on a node that used to have access but no longer does after a topology change.
So Kubernetes 1.35 makes persistentvolume.spec.node affinity mutable. KEP 5381, currently in alpha.
Release timeline. Alpha in 1.35, beta in 1.36 expected April 2026, stable in 1.38.
The change is simple. Administrators can now edit the persistentvolume.spec.node affinity field. Only admins can edit PVs. That's an RBAC requirement. So this is a controlled operation.
Feature gate, mutable PV node affinity. Let's look at an example. You have a PV with node affinity that says topology.kubernetes.io/zone in US East 1A. That's a zonal volume.
After migrating to a regional disk, an admin updates the PV. Kube-control edit PV example-PV. Change the node affinity match expressions to include US East 1B and US East 1C in the values list.
Now the scheduler knows the volume is accessible from all three zones. Pods using this PV can be scheduled on nodes in any of those zones.
This enables several real-world workflows. Zonal to regional migration for high availability, node pool migration when you're changing instance types or moving to different availability zones, disaster recovery setups where you update affinity after volume replication is configured, cost optimization where you migrate volumes to cheaper storage tiers in different regions.
Now, here's the tricky part. There's a race condition when you tighten node affinity, meaning you make it more restrictive.
Let's say a PV is currently accessible from zones A, B, and C. An admin updates the PV to only zone A, removing B and C. But the scheduler maintains a cache of PV information for performance.
The scheduler cache updates eventually, but it's not instant. There's a small window where the scheduler has the old affinity showing zones A, B, and C, but the API server has the new affinity showing only zone A.
The scheduler places a pod on a node in Zone B using the stale PV information. The pod gets scheduled, Kubelet tries to attach the volume, but the volume is no longer accessible from Zone B. The pod gets stuck in container creating state.
The mitigation currently under discussion is kubelet validation. When kubelet tries to attach a volume, it checks whether the current node satisfies the PV's node affinity. If not, it fails the pod startup with a clear error message.
The pod enters failed state, the scheduler retries on a different node that satisfies the current affinity. It's not silent failure, but it is a transient scheduling failure.
The important distinction, relaxing affinity is safe. If you add zones to a PV's node affinity, making the volume accessible to more nodes, there's no problem. The scheduler might place a pod before the cache updates, but the volume is accessible from that node.
Restricting affinity is risky. If you remove zones, making the volume accessible to fewer nodes, you can hit this race condition where the scheduler places a pod on a node that no longer has access.
Best practice. If you need to tighten affinity, cordon the nodes in the zones you're removing first. Wait for all pods using that PV to drain from those nodes. Then update the PV affinity. Then uncordon if needed.
That way, you ensure no pods are running on nodes that are about to lose access, and the scheduler won't place new pods there because the nodes are cordoned.
So how do you actually enable these features? Prerequisites, Kubernetes 1.35 or later cluster, and admin access to the API server configuration.
For extended toleration operators, add the feature gate to your API server flags. Feature gates equals extended toleration operators equals true.
For Mutable PV Node Affinity, feature gates equals Mutable PV Node Affinity equals true.
And then restart the API server. In managed Kubernetes, this depends on your provider. GKE, EKS, AKS all have different mechanisms for enabling alpha feature gates. Check your provider's docs.
Let's walk through designing a heterogeneous GPU cluster using extended toleration operators.
Step 1. Node tainting strategy. You have 3 types of nodes: 2 GPU nodes, 4 GPU nodes, 8 GPU nodes.
Taint the 2 GPU nodes, kube control taint nodes node 2 GPU, GPU count equals 2, no schedule.
4 GPU nodes, kube control taint nodes 4 GPU, GPU count equals 4, no schedule.
8 GPU nodes, kube control taint nodes 8 GPU, GPU count equals 8, no schedule.
Then, a small inference workload that's optimized for 2 GPUs specifies operator equal value 2. This matches only 2 GPU nodes.
A standard training job that needs at least 4 GPUs specifies operator LT value 4. This matches 4 GPU and 8 GPU nodes, but not 2 GPU nodes.
Wait, we established earlier that the LT semantics is about less than, meaning the taint is greater than the value. So LT value 4 matches taints with value greater than 4, which would be only 8 GPU nodes, not 4 GPU nodes.
Right. The semantics are tricky. Let me correct that. For at least 4 GPUs, you'd want a toleration that matches GPU count 4 and GPU count 8. That's probably a GT operator where the toleration value is less than the minimum you need.
Actually, let's think about this differently. If we use GT with value 3, that means I can tolerate nodes with GPU count greater than 3, which matches 4 and 8.
That works. Toleration operator GT value 3 matches GPU count 4 and GPU count 8.
And for a large training job that needs 8 GPUs, operator GT value 7, which matches only GPU count 8.
Or operator equal 8 for an exact match.
Step 3. Add an SLA layer for cost optimization. On-demand nodes get taint SLA equals 100, no schedule.
Spot nodes get taint SLA equals 90, no schedule.
Now you can combine tolerations. A batch job specifies 2 tolerations.
Operator GT value 3 on key GPU count, which matches 4 and 8 GPU nodes, and operator GT value 85 on key SLA, which matches SLA 90 and 100.
Result: the pod can schedule on 4 GPU or 8 GPU nodes in both spot and on-demand pools. The scheduler picks the cheapest available, which is likely spot instances.
If spot capacity is exhausted, it falls back to on-demand, and if a spot node gets a termination notice, the taint update to SLA equals 0. Pods get evicted based on toleration seconds, and they reschedule on other nodes.
All declarative, no custom controllers needed.
Now let's talk about a real-world storage migration using Mutable PV Affinity. Scenario: you're running Postgres SQL on a zonal EBS volume in US East 1A. You need to migrate to multi-AZ for high availability.
Before migration, the PV has node affinity saying only US East 1A. The stateful set has pod affinity or node selectors restricting pods to nodes in that zone. No high availability. If US East 1A has an outage, your database is down.
Step 1. Use Volume Attributes class to trigger CSI migration if your CSI driver supports it. AWS EBS CSI driver can migrate IO2 volumes from zonal to multi-AZ.
Step 2. The CSI driver performs the migration. This happens live, no downtime. The volume is now accessible from US East 1A, 1B, and 1C.
Step 3. Update the PV node affinity. kubectl edit PV Postgres PV. Add US East 1B and US East 1C to the zone match expressions values list.
Step 4. Update the stateful set pod affinity or node selectors to allow multi-zone placement. You might use pod anti-affinity to spread replicas across zones.
Step 5. The next time a pod restarts or you scale up, the scheduler can place replicas in US East 1B or 1C. You now have multi-AZ high availability.
Zero downtime migration. The database stayed online throughout, and critically, the PV metadata now matches reality.
Testing checklist before you do this in production. Deploy Canary workloads with new tolerations in dev and staging. Monitor scheduler decisions with kubectl describe pod, check the events and the node where it landed. Test eviction behavior with no execute taints. Manually taint a node and watch pods get evicted based on toleration seconds. Validate that PV affinity updates don't break existing pods. Update a PV in staging and ensure running pods aren't affected. Measure scheduler cache propagation latency. How long after you update a PV does the scheduler see the new affinity?
These are alpha features. Treat them as experimental until they reach beta or stable.
Now let's step back and talk about the bigger picture. These features are part of a larger trend. Kubernetes is evolving from reactive feedback loops to proactive, predictive infrastructure.
Current state of Kubernetes is reactive. HPA reacts after a CPU spike occurs. Cluster autoscaler adds nodes after pods are pending. Eviction reacts after node crusher. Storage has static affinity that can't adapt to migrations. Everything is a feedback loop. Problem happens, system reacts, eventually becomes stable.
Emerging capabilities are predictive. Workload-aware scheduling in Kubernetes 1.35, currently in beta, means the scheduler considers past scheduling decisions and learns from failures. If a pod repeatedly fails to start on certain nodes, the scheduler avoids those nodes for future pods of that type.
Predictive autoscaling, which is being developed by third-party tools and may eventually be native, uses ML models to forecast demand and scale preemptively. Instead of reacting to load at 9 a.m., it scales up at 8:45 because it learned that traffic spikes every weekday at 9.
Extended toleration operators enable threshold-based placement before workloads start. Instead of scheduling a pod and then evicting it when you discover the node doesn't meet SLA requirements, you prevent the bad placement from happening.
Mutable PV affinity lets storage topology adapt dynamically as infrastructure changes. Instead of static zonal volumes that require manual intervention to migrate, the platform reflects reality.
We're moving from react to problems to prevent problems by anticipating changes.
The role of machine learning and AI ops here is pattern recognition. Historical data identifies that every time a certain configuration is deployed, capacity issues occur within 2 hours. The system alerts before the issue happens or auto-remediates.
Anomaly detection catches configuration drift that commonly leads to incidents. Autonomous remediation means self-healing clusters fix issues while teams sleep. Reinforcement learning for autoscaling provides learned anticipation. The system observes trends, delayed system response, and adjusts policies.
This is what people mean by self-driving infrastructure, clusters that silently correct inefficiencies without requiring human intervention.
So what should platform engineers be watching?
Kubernetes 1.36 in April 2026, extended toleration operators will likely move to beta, enabled by default. Mutable PV Affinity will also move to beta. We'll see more workload-aware scheduling improvements.
Beyond 1.36, watch for integration with AI ops platforms, native predictive autoscaling that goes beyond reactive HPA, and scheduler plugins for custom ML-driven placement policies.
The scheduler is becoming smarter, storage is becoming flexible, the platform is learning.
And this represents an operational mindset shift. The old mindset was set up static infrastructure, define hard boundaries, react to issues as they occur.
The new mindset, design adaptive systems, define thresholds and policies, let the platform optimize within those boundaries.
Extended toleration operators let you say, here are my SLA requirements, scheduler, figure out the best placement. Mutable PV Affinity lets you say, storage evolved, update the metadata to match. You're defining intent, not micromanaging every scheduling decision.
It's a shift from imperative operations to declarative policies. You're not saying, schedule this pod on node 17. You're saying, schedule this pod on a node with SLA above 95 and GPU count at least 4, and the scheduler handles the rest.
And when conditions change, spot termination notices, storage migrations, node additions, the platform adapts automatically based on those policies.
All right, let's talk about what platform engineers should actually do now.
If you're running Kubernetes 1.35 or later, enable these feature gates in dev and staging, not production. Test with non-critical workloads first, audit your heterogeneous clusters, and identify where numeric tolerations would simplify operations. Document your SLA tiers if you're using spot instances, formalize risk levels as numeric taints, review storage topology, and identify volumes that could benefit from regional migration.
If you're on older Kubernetes versions, plan for Kubernetes 1.36 beta. These features will likely be on by default, so prepare your workload tolerations in advance. Audit your node affinity complexity and flag places where numeric tolerations would simplify your configs. Engage your CSI driver vendors and ask about regional disk migration support. Make sure your storage infrastructure is ready.
Common pitfalls to avoid. First, toleration operator confusion. The GT and LT semantics are about what the pod can tolerate, not direct numeric comparison. Test thoroughly, because getting the operator wrong means pods scheduled on the wrong nodes.
Document your taint and toleration strategy clearly. Future you or your teammates will thank you when they're debugging why a pod didn't schedule where expected.
Second pitfall, PV affinity race conditions. Relaxing affinity, adding nodes, is safe. Tightening affinity, removing nodes, has race condition risk. Always cordon nodes before tightening PV affinity, wait for pods to drain, then update the PV.
Third pitfall, alpha feature risks. Don't use these in production without extensive testing. APIs may change between alpha and beta. Have a rollback plan, which usually means disabling the feature gate and restarting the API server.
The long-term vision here is that these features are enablers. They let you build platforms that adapt dynamically instead of requiring manual intervention.
Today, you have static node pools, manual scaling decisions, fixed storage topology, complex node affinity rules, custom scripts for node draining.
With these features, threshold-based placement, dynamic storage migration, cost-optimized scheduling, declarative eviction policies, simplified operational overhead.
In the future, autonomous platforms that optimize cost, performance, and reliability without human intervention. The platform learns your workload patterns, anticipates changes, and self-optimizes.
You're not just scheduling pods, you're defining policies for an adaptive, self-optimizing system.
To wrap up, Kubernetes 1.35 introduces two powerful alpha features. Extended toleration operators bring numeric comparisons to scheduling, enabling threshold-based placement for GPU clusters, spot instances, SLA-based scheduling, and performance guarantees.
Mutable PersistentVolume Node Affinity lets storage topology adapt as volumes migrate from zonal to regional or change accessibility.
Both features address real operational pain points. No more complex node affinity workarounds for heterogeneous clusters, no more stale PV metadata after storage migrations. These simplify operations and enable dynamic, adaptive infrastructure.
Start testing these in non-production environments now. Enable the feature gates in 1.35. Experiment with numeric tolerations on dev clusters. Try PV affinity updates in staging. Prepare for beta in 1.36 when these features become enabled by default.
And remember the bigger picture. These are part of Kubernetes evolving from reactive to predictive. Your role as a platform engineer is evolving too. You're moving from manual operations to defining policies for adaptive systems.
Want to dive deeper? Check the show notes for links to KEP 5471 for extended toleration operators and KEP 5381 for mutable PV affinity. The Kubernetes 1.35 release blog has detailed examples and API references. And if you're running heterogeneous clusters or multi-zone storage, start planning your migration strategy now.
That's the picture for Kubernetes scheduling and storage in 1.35.
If this breakdown helped you understand these new features, subscribing helps us know to make more content like this. That's it for today's deep dive. Stay ahead, stay curious, and keep building platforms that adapt.